general relativity, step by step. We've got the Einstein field equations here, which are undetermined up to this constant, cosmological constant lambda here. And this k here, which I'm going to talk about today. So I'm going to find k. It's just a constant. And it's a constant which depends upon the units that we choose to measure it. But I want the field equations here to reduce to Newtonian dynamics. And when I say reduce to Newtonian dynamics, in the case of weak fields, so we've got no neutron stars, no black holes, so e.g. the solar system, and slow speeds, slow compared to the speed of light, much, much less than the speed of light. Well, is it better reduced to Newtonian mechanics, or we've got a serious, serious problem, because as we all know, Newtonian mechanics is supremely successful at describing the dynamics of the solar system. And I guess the perihelion advance of Mercury is a case in point. That's a tiny, tiny, tiny perturbation to Newtonian mechanics. And it's very, very, very small, and it's only on the most extreme parts of the solar system that you need this. And the perihelion advance of Mercury is a very, 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 very tiny effect. It's of the order of a few kilometres. The perihelion moves forward by a few kilometres each orbit, which is a very, very small distance compared to the other distances we consider. So I'm going to find k, which is a constant. And of course what we're doing here is we are using the field equations to link the curvature of space with the matter density, stress energy tensor given by this T thing here. So we'd expect k to be a little bit difficult to identify, simply because we're dealing with two very, very, very different objects on the left-hand side and the right-hand side. Here we've got properties of space, and here we've got properties of matter. So we'd expect there to be some fundamental constant linking the two. Okay, so how do we proceed? Well, the first thing is to identify what we mean by weak field. So I've got my metric tensor. Here's my metric tensor. I'm going to assert that it's equal to eta mu nu plus h mu nu. Let me tell you what these things are. This thing, I didn't mean red. Let me go back to, sorry about that, that's a little glitch in my recording here. Where was I? Fundamental tensor, metric tensor, equals eta, which is this 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, plus something small. So what I'm asserting is that all elements h mu nu is the modulus of these guys is much, much less than 0. Okay, so that's what I mean by weak fields, and we'll introduce this slow movement approximation where we need it. It's important to say that there exist coordinates, coords, with this property, g mu nu equals eta h. No, got an h in the wrong place. Mu nu plus h mu nu. There exist coordinates. It's not the case for all coordinates, because of course I might choose to describe the solar system in terms of r theta, polar coordinates, which don't have this nice property here. So there exist coordinates. So what I mean to say is that I can construct an elevator, and inside my elevator, even though the elevator might be falling into the sun, I'm going to ignore that and just construct a local inertial frame in which I've got my nice metric tensor here, with non-zero second derivatives, of course. I'm also going to assume that the field is stationary. So what that means is that the time derivatives di h mu nu by di x 0 are equal to 0. We haven't got any time component in here. We haven't got any, there's no equals 0. There's no oscillating gravitational field here. There's no switching backwards and forth. You haven't got two black holes orbiting around each other. You have got a stationary field. And the way to think about it is that the sun isn't moving anywhere, and that's just sitting there. So we've got these assumptions here. I haven't quite formalised a slow motion assumption yet, but we'll come back to that in a minute. So what is the behaviour of test particles? What's the behaviour of test particles? Test particles are small enough not to affect the field and not to violate our assumptions here, either about the weak field or the stationarity of the field, I guess. Okay, well, let's start out with the geodesic equation. d2x mu, I'm just copying from my notes here, by di tor squared, plus Christoffel symbol mu sigma dx mu by d tor dx mu by d tor equals 0. And that's my geodesic equation. Even now, it's a matter of some surprise to me that how much, this is a very complicated equation here, how much we can simplify this equation by our weak field, slow-moving particle approximation. Lots and lots and lots of terms will disappear, and that'll make our lives a lot easier. Okay, so what does moving slowly mean? Well, if I define t equals cx0, where c equals the speed of light, then what I'm trying to say is that dxi by d tor is much, much less than dx0 by d tor for I equals 1, 2, 3. You'll notice I'm using the convention that Roman letters like I and J and K go over 1, 2, 3. If I want to have the 0 in as well, then I'll use a Greek letter like mu or pi or something like that. But the Roman letter I refers to summing over the space-like coordinates, space-like indices. So basically, we can ignore the three velocity in the geodesic equation. And what are we left with? What are we left with? Well, let's have a look. We've got di2x mu by di tor squared plus, now if we look at the summation here, basically what's left, I'm only going to consider the terms that are important. So basically, because of this rule here, it means that in this equation here, I can just assume that mu equals 0 because the other terms are very, very small, so I'm going to ignore them. So let me just pinch in a little bit so you can see both of them. So what is left is mu and then 0, 0, because I'm assuming that mu and sigma both are equal to 0 because only the 0 component of these terms here counts for anything at all. And what have I got left? Di x 0 by di tor, di x 0 by di tor equals 0. I'm casually using 0 to mean two different things. I'm using it as an index here to refer to the time-like coordinate, and here as well, I guess. Equals 0, which is just a number that means nothing at all. Okay, so that tells me, let me just pinch in a little bit, d2x mu by di tor squared plus Christoffel symbol mu 0, 0 times di x 0 by di tor squared equals 0. And I've defined, in order to make this equation here make sense, I've defined this to be the case. I've defined t to be equal to cx0. T equals x0 times c. So that tells me that di tor d2x mu by di tor squared plus Christoffel symbol mu 0, 0 times c squared times dt by d tor squared equals 0. Let me write that again. That's a little bit messy. d2x mu. You'll remember here that mu is ranging over 0, 1, 2 and 3 because it's a Greek letter, by d tor, plus the Christoffel symbol, which I'll evaluate in a minute. In fact, this has already gone on 10 minutes. I might do that next. 0, 0, times the speed of light squared, times d, which way around is it? T by d tor squared equals 0. And this is the geodesic equation, or the geodesic equations, because there's 4 equations here, one for each value of mu, as mu ranges over its range of 0, 1, 2 and 3. So hopefully we'll get some nice equations out of that, and hopefully we'll see how they match up to Newton's laws of motion. But I'm going to stop here, and I'm going to evaluate this beast here. It's not that bad, and you'll see how many terms drop out. You'll remember it's quite a complicated thing in the general case, but in this very special case of weak fields and slow speeds, we'll see that it's quite easy to evaluate. So I'll stop here and continue next time. Stop.